Okay, let's go ahead and take a look at this last section of this chapter, which is called optimization. Now, what are we dealing with when we're dealing with optimization? Is really we're trying to find out where the maximum or minimum value of your function is. Now, of course, if you have a graphing calculator, you can very easily just go ahead and find a minimum or a maximum by using the graph. But you can also approach it from a very algebraic standpoint, and the way that we do that is by using calculus. So let's go ahead and take a look at what we have here. We say that in order to find a max or a min, you need to find, first of all, where the stationary points are. So that means that you have to find out where f prime of x is equal to 0. After that, we need to go ahead and analyze and algebraically show whether or not that point is going to be, that stationary point is a max or a min. Now, how do we go about doing that using the first derivative? Now, what we know is that if we find a particular point, and let's just say that this point is a stationary point because this is where f prime of x is equal to 0. If f prime of x is positive to the left, so in other words it goes positive, the value of f prime of x is positive, 0 then negative, then that means that it looks like that. It's positive, 0, negative. That means that your stationary point is a maximum value. Now, let's go ahead and take a look at the minimum. If your f prime of x values go negative, 0, then positive, then that means that this stationary point would then be a minimum. Because the function is decreasing, hits a stationary point, then it starts to increase again, that stationary point is therefore a minimum. Now, that's how you can go ahead and determine if a stationary point is a maximum or minimum value of the function using the first derivative. If you wanted to use the second derivative, this is what you would do. You would take that stationary value, you would substitute it into f prime of x, and if it came out with a negative value, then you know that that has to be a maximum. Because what that means is that this stationary point, the concavity is down. That means that the stationary point is at the top of the function, which means that it's a max. At the same respect, if you go ahead and think about the value of the second derivative at that particular stationary point, if it is positive, then that means it's concave up. If it's concave up, then that means that the stationary point is at the bottom, which means that that stationary point is actually a minimum value of the function. So, once we go ahead and find out what f prime of x is, where it's equal to 0, we can then use the first derivative or the second derivative to determine whether or not that stationary point is a maximum or a minimum. Now, the first step, of course, is to find out what that function is. And if you can't find out what that function is, then none of this really means none of this makes any sense. Okay, so we need to go ahead and find our initial statement, which is going to be our function that which we're going to analyze. Now let's just go ahead and take a look at number 1 in the book. Okay, and this problem talks about a duck farmer. Let me just read it to you. A duck farmer wishes to build a rectangular enclosure of area 100 square meters. So notice I went ahead and drew this picture here. The farmer must purchase wire netting for 3 of the sides, as the 4th side is an existing fence of another duck yard. So here's that existing fence. Here's the 3 sides that we have to actually purchase wire for. It says naturally the farmer wishes to minimize the length, because by minimizing the length you actually minimize the cost. So we're trying to optimize. And the fencing, minimize the length of the fencing required to complete the job. So the first thing, of course, like we said here, is that you have to find out what your initial statement is. And that initial statement is going to be given to you by the actual question itself. So let's take a look. We want to actually come out with a function that is going to determine the length of the wire that's needed, the fencing that's needed. So we need to look for length. Now, I'm just going to go ahead and put this as W here, because that W represents how long that length is, because that part's not given to us. So if we go ahead and talk about the length of the fence as a function in terms of 2 variables, which is x and w, so here's x and here's w, then the length is actually just going to be 2x plus w. But the problem is that when we want to go ahead and differentiate, we have to make sure that there's only one variable. So we have to find a different relationship so that we can substitute values, substitute something in for w in terms of x. Now, how do we do that? Well, we know the other piece of information that we haven't used yet is that the area is actually going to be 100 square meters. Now, if the area is 100 square meters, we know that area is the same thing as length times width. So if we go ahead and take x times w, we get 100. So we can then go ahead and solve for w and say that w is equal to 100 over x. So what that means then is that I can change this initial statement, which is in two variables, to make it into an initial statement which only has one variable in terms of x. Okay, so what that means then is that instead of having 2x plus w, being that I know that w is 100 over x, I know that the L of x is just 2x plus 100 over x. And there you go. Now we have the function in terms of one variable x, and now we can go ahead and do the analysis here to find out how to optimize the situation. So let's go ahead and differentiate, because we said that that's the first thing that we need to do. We go 2x plus 100 times it by x to the negative 1, because we don't want to use the quotient rule. We just want to use the power rule. So L prime of x then is going to just be 2 plus 100 times by negative 1 x to the negative 2. Now, of course, we want to take that first derivative and set that equal to 0. Set that equal to 0, solve for x. And what we come out with is negative 100 over x squared is going to be equal to negative 2. That means that x squared has to be equal to 50. Then we can take the square root of both sides, and that's going to be plus or minus 5 square root of 2. Now the thing is we're actually dealing with length here. So we know that x has to be greater than 0 because there's no such thing as negative length. Therefore, x has to be 5 square root of 2. Okay, now that is a stationary point. So what we want to do now is, given that that's the stationary point, let's go ahead and use the first derivative and determine what is happening on the left and the right hand side of that stationary point. So I know that the minimum value, well, it can't be 0, so I'm just going to say 0 here. Anything between 0 and 5 square root of 2, because that's our stationary point, I just pick the value of 1, and if I substitute it into L prime of x, I come up with a negative value. If I take anything larger than 5 square root of 2, and 5 square root of 2 is about a little bit more than 7, so we'll just say something like 8 or 9, then what I come up with L prime of 8 or 9 is that I actually come up with a positive value. So notice what happens then is that the function is decreasing, stationary point, increasing. So decreasing, stationary point, increasing, that means that this is a minimum value. Okay, now let's go ahead and also take a look at how we can analyze this and show that this is a minimum value by looking at the second derivative as well. If I go ahead and differentiate the first derivative to find the second derivative, notice the 2 will disappear because that's a constant. Then this is going to be negative 100 times it by negative 2x to the negative 3. That's the same thing as 200 divided by x to the third. Now, if we were to go ahead and take a look at 5 square root of 2 and substitute it into here, that is actually going to give you a positive value. So what you know then is that the function is actually concave up. If it is concave up, then this stationary point here is actually a minimum. So there you go. This value, x is equal to 5 square root of 2, is a minimum value. If you use 5 square root of 2 for this value of x here, you can find the minimum amount of length that's needed in order to create a fence that is going to cover 10 square meters. Okay, and then if you want to go ahead and find out what that value is, you just need to substitute it into here. Okay, and there you go. That's how you can use calculus to find the maximum or minimum of a function, which means that you're actually looking for how to maximize, or how to finding the optimal situation and the optimum value for a particular context. Okay, so go ahead and try some of those problems and see how they work out. And let's see how things turn out. Okay? All right, see you next time. Bye.